In this video, we're going to use a geometric analogy to try to understand what's going on a little bit more with the product rule. So up here on the board, I've written out the limit that we need to evaluate in taking the derivative of f times g. And a couple videos ago, we spent some time doing a bunch of algebra to algebraically figure out what was going on. Now, I'm going to think of this a little bit more geometrically. If f and g happen to take on positive values, I could think of them as dimensions. One of them is the base of a rectangle, one of them is the height of a rectangle, and then their product would be the area of that rectangle. Now that interpretation only makes sense, of course, if they're positive, but it can still help me to understand what's going on. I know the product rule works even if these functions take on negative values, but this just helps me to understand it in the case that they're positive. Okay. Now, this is the derivation that's presented in your textbook, and I'm going to work through it. I'm not using exactly the same notation, though, that the book does. Just want to point that out, because I'm trying to match this, which I've written in terms of h. They're writing it in terms of delta x instead. Basically just a change in the way they're naming things. But I will follow some of their notation. They sort of give a nickname to these dimensions. So they're going to say u is f of x. So if I was thinking of f of x as the base, I can just name that u. Okay. And they're going to let v be a nickname for g of x. And if I was thinking of g of x as the height, I'm just going to label that as v. Okay. So then u times v, that would be the area of this rectangle here. Okay. And that's just f of x times g of x. So this term that I'm subtracting on the top of my limit, I can interpret now as just being the area of that rectangle. Okay. So that's my geometric interpretation of this part of the limit. So now I need to think about this part. Okay. Now, just to keep the picture nice and simple, let's suppose that f of x plus h is longer than f of x. So f of x, that was what we called u, f of x plus h would be a little bit longer. Okay. So this longer base is f of x plus h, and I'm just going to call this difference here delta u. So that delta u is the difference between f of x plus h, the longer base, and f of x, the original base. Okay. And let's suppose the same thing for v, that g of x plus h is a little bit longer than g of x. So this was the original height, g of x, which we renamed as v. We're going to think of g of x plus h as being a little bit taller. And I'm going to just name that difference there delta v. So that delta v is g of x plus h minus g of x. Okay. Now, both of these quantities are going to go to 0 if h goes to 0. Because as h goes to 0, this is getting closer and closer to f of x, and that first term there is getting closer and closer to g of x. But now, if I use those bigger dimensions, the area of this big rectangle would have its base as f of x plus h, its height is g of x plus h, so the area of the bigger rectangle is that first product that shows up in my limit. So I'm just going to shade this extra bit here in green, and then I can interpret this first term here as being the area of that bigger rectangle. The extra green stuff together with the original blue area that we had. Okay, excellent. So now what I'm going to try to do is I'm going to try to rewrite this limit, writing the top, instead of in terms of f's and g's, in terms of these new names, u's and v's. Okay. So we're still dividing here by h. Okay. But now I know that the top is just the bigger rectangle minus the smaller rectangle. That's going to be just those green parts of the area. And I can actually express that as a sum of 3 pieces. There's the area of this rectangle here, and then the smaller one up here in the corner. This rectangle has a base of u and a height of delta v. I'm going to add to that the area of the other two rectangles that make up the green area. This rectangle has a base of delta u and a height of v. I'm going to just write that as v delta u. And then this little rectangle up here in the corner has a base of delta u and delta v is the height. Okay, excellent. So now I'm going to do two things. I'm going to distribute the division by h, and I'm also going to apply the sum rule of limits to write this as three separate limits. So we're looking at the limit as h goes to 0 of u delta v over h, plus the limit as h goes to 0 of v delta u over h, plus the limit as h goes to 0 of delta u delta v over h. And each one of these I can interpret as an area of one of these green rectangles divided by h. Now, if I take a look at this, first limit, u, we said was just f of x. There are no h's in that. So u is constant with respect to h, which means I can just factor that out. So that's going to be u times the limit as h goes to 0 of delta v over h. Okay. Now, let's take a look at what this means. I'm going to go back to writing things in terms of f and g. Now, of course, I've still got to do this with the other two limits, but I'm going to go ahead and take this one step further. U, we said, was just f of x. Delta v was g of x plus h minus g of x. If I put that over h, I'm getting the difference quotient for g. When I take the limit, I'm getting g prime. So when I take the area of this rectangle, divide by h and take the limit, that gives me this term that shows up in the product rule. Let's move on to this piece, which was this rectangle divided by h. Okay. Now, v was just g of x. Once again, there are no h's there, so that's constant with respect to h, so I can factor it out. So that's v times the limit as h goes to 0 of delta u over h. But what was delta u? F of x plus h minus f of x. When I put that over h, that's the difference quotient for f. That's the formula for the slope of the secant line connecting 2 points on the graph of f. When I take this limit, that's going to give me f prime. And v was just g of x. So this gives me g of x times f prime of x. This piece, the limit of the area of this rectangle divided by h, gives me the second term that shows up in the product rule. Now what about this piece? Well, this is the limit as h goes to 0, and I've got delta u, delta v, and h here. What I'm going to do is I'm just going to rewrite this as delta u over h times delta v. I chose to associate the h with the delta u at a 50-50 choice. It's 6 of one, half dozen of the other. I could have just as easily associated the h with the delta v. That would be totally fine. But the product of this fraction with delta v is the same as this fraction right here. I'm still multiplying delta u and delta v on top and dividing by h on the bottom. Okay. Now I can apply the product rule of limits here. This first piece, delta u over h, we saw that's just going to go to f prime of x. Let's see. Delta v is going to go to 0. Because we said both delta u and delta v go to 0 as h goes to 0. Now, I paired up one of them with the h so that that ratio actually went to the derivative, but that leaves the other one. I didn't have a second h to associate with it, So this third piece is going to go to f prime of x times 0. If I'd associated the h with the delta v, it would have gone to 0 times g prime of x. Doesn't matter. That third piece is going to 0. Okay. So essentially, I've got these 3 rectangles that together make up the top of this difference quotient. These two, when I divide by h and take the limit, each of them contributes one of the terms that I get in the product rule. This one, because both the base and the height are going to 0 here, that one, when I divide by h, the whole thing is still going to 0, so it doesn't contribute anything. Kind of a neat way of thinking about things.